Video 3 of 6 on day 7, talking about trees. This video is going to be about some traversals. So, trees are useful data structures. Data structures are useful in as much as you can process them. So, how does one work with trees? What kind of programs do people write over trees? One of the simplest programs you can write on a tree is called a traversal. So any function that looks at every node of a tree is called a traversal. Now, people often, when they say the word traversal, mean in particular the process of converting a tree to a list in some way, but not always, right? A traversal is anything that looks at all of the tree. But here we're going to look at three different ways to convert a tree to a list. Okay, so there are three common notions of traversal. You could do other ones, but these are the most common. So I'm going to do them in what I think is the most sensible order. Pre-order says when you get to when you're looking at a node, do the node's value first, then traverse the node's left children, then traverse its right children. Okay, that gives you one ordering of how trees might work. An in-order traversal says no. First do the left children, then do the value, then do the right children. And a post-order traversal says no, do the left child, then the right child, then the value in the node. You could do others, right? You could have a post order where you did the right first. But all of these go sort of left to right because these were sort of designed by English speaking people and English goes left to right, is I think my guess. Okay, so here's an in order traversal. Let's take a quick look at this function. So, as promised, it takes a binary tree holding some kind of value and it turns it into a list. You can think of this process as serialization. What does that mean? Well, serial means in order. So a tree has all of this structure of, nodes and their children and all the leaves and everything. But a list just says one thing after another. So to take a tree and to put it in a flat list is to serialize it, is to put it in some order. So in order traversals say, okay, well, if the tree is empty, then there's no list. Otherwise, if I get to a node, in order says I'm going to do the tree in order from left through the node to right. That's how I'm going to traverse the tree. So we'll do an in order traversal of everything on the left, and then we'll put the value in the middle, and then we'll do an in order traversal of everything on the right. So I want to note a lot of the functions we've written so far have tended to just use cons to construct lists, but here we're using plus plus. That's append, right? Right. This is the thing that smashes two lists together. You might also wonder, well, if this is just one value, why do we need to put a singleton list? But look again at the type of app. App takes list x arrow, list x arrow, list x. So this is going to be some list of capital X's. This would then need to be a list of capital X's, and so would this. So we'll put it in the singleton to say, like, hey, what are we stuffing in the middle? Just this one thing. So if we use this as our running example of the kinds of trees we're interested in, what would an in-order traversal be? So remember, it goes left through the node and then right. Think about it for a second. See if you can figure it out. 12, 25, 5, 5. So why is that? Well, let's do a little quick computation using our substitution model of evaluation. Okay, well, that's going to be in order, and then whatever's here on the left, then whatever's here on the right. Sorry, I'm not in KeyCast mode. I haven't yet typed anything fancy, but sorry to forget to turn that on. Okay, well, if we look at this, well, this is going to be, let's do the left one first. That's going to be in order empty. We will leave the parens there just to make it clear that all that's going to happen first, if we like. Okay, well, this is going to be empty. That's going to be empty. Okay, so that's just going to, ooh, whoa, pardon me. That's just going to be 12, 25. Let's continue on the right. That'll be that. That. Okay, keep going. Okay, now at this point we can kind of collapse the whole stack, and this will just be 12, 25, 5, 5. So I went a little fast, so you might want to slow down the video there if any of that got a little confusing. Sorry about the wonky edits. Um, if you don't feel comfortable with this, we should definitely talk, right? Like this kind of like, oh, let me run the function step by step. Um, we're not at second nature yet. So for me, it's second nature. I've been doing this for a long time. But for you, it should be comfortable. If it's not comfortable, if you're unsure what step to do next, or sort of like what the right thing to do is, or what it means to substitute arguments in, we should definitely clear that up as soon as possible. Make sure you have a really clear evaluation model for how these programs are. Okay. So your homework is to write the pre-order and post-order traversals. Okay, define those. Shouldn't be too bad. You've got a nice model right here in order, sort of telling you like what the score is. Right? So not too bad there. And then we'd like you to write what are not quite unit tests, but sort of demonstrations of your understanding of how these traversals are different. So for different all three, we want you to write a binary tree holding bases that's going to have different output from all three traversals. Right? It should have at least 3 nodes. And then in order should produce one list, and post order should produce another list, and pre order should produce yet another list. None of them should be the same. Okay. Next, we want you to have a tree that's the same in pre and in order, but different in post order. Again, holding bases, DNA bases. And then lastly, something that's the same in post order and in order, but not the same in order, in pre order. Right? Post and in order are the same. Pre order is different. So just like you'll just write a little definition of binary trees for each of these. On all of them, we want them to have at least 3 nodes, and then they should have this property. We'll be testing that bit automatically. Please do not change the type. Right? It's important that the type stay exactly the same. Okay, that's it for traversals. Questions on Zulip as usual. After this, we'll be talking about a super interesting and important data structure called binary search trees that use binary trees to write some really interesting and useful algorithms. So that's pretty exciting. It'll be our first sort of really serious data structure we're looking at with cool invariants and stuff. Okay, talk to you soon.